Hey AP Calculus students, this video is going to cover the remaining two cases of indeterminate form that we didn't have a chance to wrap up in class. So the first problem is one that we had started on. This is the 0 to the 0th power version of indeterminate form. So when we try to evaluate this limit by plugging in 0, the inner expression is 0 and the exponent is also 0. So I'm going to copy this expression over here so that we have some room to work. So we're looking to take the limit don't know what's going on there. Limit as x approaches 0 of 1 minus cosine of x, all raised to the x power. Now with these ones, you want to set them as equations because ultimately to get the exponent out of where it's located, we're going to have to take natural logarithms. And we have to do that on both sides. So here I'm going to take the natural logarithm of y, and I'm still working with limits, so I need that information out in front. And then I can take the natural log of 1 minus cosine of x to the x power. This allows me to rewrite this information in front here. So now I'll have x times the natural log of 1 minus cosine x. At that point, I'm still not in a form where I can benefit from L'Hopital. I need a fractional setup. So what I can then do is bring that x down to the bottom part of the equation by making the exponent on it negative. From there, this is where I'm in the 0 over 0 case for L'Hopital, because natural log of 1 minus cosine of 0, 1 minus 1 would give me that value. And then I've got a 0 down below as well. So what I then am going to have to do is to figure out what derivative I have up top and what derivative I have down below. So when I go to take this expression, derivative of natural log of 1 minus cosine of x, that's going to give me 1 over 1 minus cosine of x, and then the inner derivative is going to be the positive sine of x. The bottom function's derivative is going to be negative 1 x to the negative 2 power. Now if we think about the way things are currently set up, if we just progressively keep taking derivatives on this expression down in the bottom, it's always going to be a 0. So before I go to take my next derivative, I probably want to play around with the way this equation is set up algebraically. I can bring this negative exponent back up to the top part by calling this negative x squared times the sine of x, all divided by 1 minus cosine of x. So again, still an indeterminate form, but then I can just apply L'Hopital's once more, and then I have another round of derivatives to take. So this was really my first iteration of L'Hopital. Now I'm going to do another instance of L'Hopital here. When I go to take this derivative, I'll have negative 2x times sine x because I leave that as a non-derivative. Then I leave my first expression alone, and I'll have the cosine of x here. Down in the bottom, when I go to take that derivative, this 1 will go to 0. Negative cosine of x will become positive sine of x. At that point, I still need to figure out what I'm going to have on the top and on the bottom. Here, this is going to be another 0. This is going to be 0 as well. The one remaining issue, though, is that this sine of x is also going to end up being a 0. So I'm probably going to have to take one more iteration of L'Hopital because that's going to get me to a cosine on the bottom, which means I would no longer end up with division by 0. So let's see what that turns out to be. Up top, we'll have negative 2 sine of x minus 2x cosine of x minus 2x cosine of x plus x squared sine of x. So all of that happens up top. Then down on the bottom, take the derivative of sine, and we end up with cosine of x. So here, this negative 2x cosine of x and that negative 2x cosine of x are going to become negative 4x cosine of x. And then we can see what else we're going to get. Here, negative 2 sine of 0, that's going to go to 0. This expression goes to 0 because it has an x in it, and so does this one. So we're just going to end up with 0 divided by 1, which is 0. Then what I need to check out is this is equivalent to the natural log of y, because that's what we set it equal to all the way back up here. So I have the natural log of y is equal to 0, I need to make both sides exponents of the natural exponent e. So y is equal to e to the 0 power, or 1. And that's going to be our final answer here, which is kind of a nice result. So I did have to get through L'Hopital's 3 times there. That one's a little bit extensive. But you have another good example of this one in your textbook on page 574, where you're just working with sine by itself. So if you'd like to see another example of this one, that one goes by a little bit more efficiently. So again, this final answer here is just 1. Then we have one additional case of L'Hopital, this case number 6 of the indeterminate form. And this one pops up when you're trying to evaluate a logarithm and you end up with subtraction of infinities. So let's copy this over and work through it and see what that means to try to subtract infinity from infinity. And if you can just fix this common log of x to look like a natural log of x, that will make our differentiation process look easier. So here we'll have the limit as x approaches 1 from the right of, we've got x over x minus 1 over the natural log of x. So with this problem here, what we mean by subtracting infinities is if I go to plug 1 from the right into my first expression here, I'm going to end up with infinity. And if that was just my regular limit, that would be fine. If I just looked at that fraction, infinity, I'm good to go. If I come over to this expression, 1 divided by, as natural log approaches 1 from the positive, it gets closer to 0, so the whole expression gets closer to infinity. So I end up with infinity minus infinity there. Now, we don't know which infinity is stronger, so we don't necessarily know what the value is going to go to, because if they weren't exact quantities, they're not going to end up at 0. So when you have two fractional values where the limit of each one separately would go to infinity, you need to handle that by getting them common denominators and working from there. So let's see what that looks like. Here, this will be the limit as x approaches 1 from the positive. And to get common denominators, I'm just going to multiply whatever I don't have up to the numerator. So this will be natural log of x minus 1, because that's just being multiplied by 1. Oops, I forgot my x out in front there. X times the natural log of x. And then down here, I've got x minus 1 times the natural log of x here. Now this is still going to be in L'Hopital's, but now it's going to be in 0 over 0 indeterminate form. We're no longer in infinity minus infinity. So at this point, we want to go ahead and take our derivatives top and bottom and see what outcome we get there. So here, x times natural log of x, I'm going to have to use product rule there. So my derivative will turn out to be 1 times the natural log of x, then plus x times 1 over x. And then we've got a minus x, so we've got a minus 1. This constant will just go to 0, so we don't have to worry about that. Then down on the bottom, here we have x minus 1 times the natural log of x. So, oops, I just copied that down. We need to get the derivative of that. So here, this derivative is just going to be 1 times the natural log of x, and then plus x minus 1 all over x. Oh, oh no, I've got that right. Okay, sorry, I was losing track of my fractions there for a second. Now here at this point, we want to go ahead and simplify because this is going to go to positive 1. 1 minus 1 goes to 0. So this expression just becomes the natural log of x, all divided by the natural log of x plus x minus 1 over x. Now we don't really want fractions and fractions and fractions, so to get rid of this denominator down here, let's just multiply top and bottom by x and see what we get there. So this now becomes x natural log of x up here. Down below we've got x natural log of x plus x minus 1. Now we're still in indeterminate form because we are going to end up with, right here, 1 times 0, so 0. 1 times 0, 0, plus 1 minus 1 is 0. So we've got another 0 over 0. So that means we need to L'Hopital for a second time. So I'll go ahead and mark that here, which means we have one more set of derivatives to take. So here, this is going to be 1 times the natural log of x up top as I use product rule, then plus x times 1 over x. Down below, Same scenario, I've got x times the natural log of x. So that's going to become 1 times the natural log of x plus x times 1 over x. And then I've got a plus 1 here from this expression. What I want to do next then is to figure out, okay, I've got 1 times the natural log of x plus x times 1 over x. So this is going to become the natural log of x plus 1. Down here, I'll get the natural log of x plus 2 because this expression also goes to 1. 1 and 1 gives us that 2. Now, as we approach positive 1 in this limit, I'm going to end up with a 1 here. Natural log of 1 is 0. Natural log of 1 is 0 down here. So my final answer here is just going to be 1/2. So my final result that I can report back on this slide is 1/2 as well. So that's the case of infinity minus infinity. Those are all of the cases of indeterminate forms we'll look at with L'Hopital's rule. So what you want to take away from these expressions are, if you have infinity subtraction, go ahead and get common denominators and L'Hopital as many times as is needed from there. From the previous case, anytime you've got functions in the exponents, whether it's just a regular x or a trig function or another logarithm, use natural logarithms to bring that exponent out in front. Tonight's homework, if you find on your last slide, is going to come from the first regular part in your textbook, then the review part in your textbook, and then a linked section online that will give you a chance just to practice with a little bit of multiple choice in addition to the regular problems. That's all for L'Hopital. We will come back on Tuesday and we will talk about how you find derivatives of inverse functions and how the slopes of inverse functions compare to one another. Thanks, guys. Have a great weekend.